Hello, my name is Larry Purcell. I'm an agricultural scientist with the University of Arkansas System Division of Agriculture. And today we're at the Milo J. Schultz Agricultural Research and Extension Center in Fayetteville. I'll be talking today about research that Trent Roberts and I have been doing to look to see if corn in early vegetative stages needs additional nitrogen. We'll do this with two different methods. We'll look at the leaf nitrogen concentration, and we'll also look at aerial images taken from a drone to measure the intensity of greenness. The drone that we're using is a DJI Phantom 4 Pro. This drone is directly off the shelf without any modifications. It's been a very stable platform for us. It has a very nice camera that takes excellent quality images. It cost roughly around $1,500 with the case and with extra batteries and everything that you need to fly. The only thing that you do need is an iPad mini that goes along with the transmitter. And as part of the Division of Agriculture, we have to have an FAA license in order to fly. And as a commercial operator on a farm, you would also need to have an FAA license to fly. The main things you need to think about are you want to make sure you're in an airspace that's appropriate to fly, that you're below 400 feet, and that you can always see the drone. There are several other things that you would need to know, but those are the primary things. The software that we use is called Ground Station Pro. It's also a product of DJI and is freely available. And it basically looks a lot like something that you would see from Google Maps. You pull a map up on the screen, you're able to zoom into your farm, and on the image that I'm showing you now, it will show the exact spot on the research farm here in Fayetteville where we'll be flying our field. You can move the corners of this field to exactly where you want it, and then you can plug in, using the software, your altitude, the amount of overlap you want to have between images, and then everything else is ready to go. All you have to do at that point is just press the fly button and it's ready to take off, and that's where we are right now. So we're transmitting the data to the drone at this point. We're ready to fly, and I just have to press the button, and so the drone will be flying at 100 feet. It will make 3 passes across the field. It will take roughly 3 minutes to do this. And during that time period, it will be taking an image every 2 seconds. And so as it's flying now, if we look down from the drone at this point, we can see the bird's eye view of what one pass looks like as it goes across the field. The images that we take here today are obviously in a cornfield that is well past early vegetative stages, but the images I'm showing you are from images taken earlier in the year when the corn was between V6 and V12. So it's completed 1 pass now. It's about to come back on a 2nd pass. The drone uses batteries as its energy source. On 1 full battery charge, it can fly around 25 to 26 minutes. And with this drone flying at 400 feet, the maximum altitude that you're allowed to fly, and with about a 60% overlap, a farmer or a consultant could roughly cover somewhere between 80 and 100 acres, depending upon field dimensions and layout. So even though we have a relatively inexpensive drone running on a battery, it's still able to cover quite a bit of area in its flight pattern. Looking at the drone now, it is beginning its final pass in the field. Everything up until this point has been completely autonomous. I haven't done a thing other than program it initially in the laboratory in my office. And when it finishes its mission, it will hover in place and I'll land it manually. We've collected our data and we're ready to go back to the laboratory now to pull the images off of the drone and begin to analyze those images on the computer and see what these results really mean. We have taken our drone from the field back to the laboratory and taken the SD card out of the drone and have uploaded those files to a computer, and we are now stitching those images together in the using the software that I've got illustrated on the screen now. And what you see are the individual pictures that were taken in the field, and they are placed in their proper position on the field, over the field, based upon their GPS coordinates that are embedded in each image. The software that we're using is Metashape, made by Agisoft. It does a really nice job. There's lots of other programs that can be used either on your computer or in the cloud. I know Drone Deploy has a free service that allows you to stitch images together. So many different images can be stitched together per month. And then there's a pay service if you go above that number. But it does a really nice job. And this picture here, this screen capture, shows a little bit better where the images are located, shows an elevation. These were all taken at 100 feet above ground level, shows their position in the field. And the stitched image looks like this, and you can see the dark green patches in the field representing the plots where nitrogen has been applied, and the yellow portion of the field where insufficient nitrogen has been applied. So once we have our stitched image, we now straighten that image and using software, and then we import it into another software program called Field Analyzer. And this is Field Analyzer, a screenshot from it. And Field Analyzer allows you to select the number of rows that we have. In this case, we have 6 rows in this portion of the field, and the number of columns, 1, 2, 3, 4, in this portion of the field that we want to analyze. And then by double-clicking on one corner of the field and dragging it over to the other portion of the field, it selects the plot areas, and from that it extracts the data that we'll use for the DGCI values. So it's as simple as that. The DGCI values are then stored in a Excel type sheet, a spreadsheet that we can analyze just like we would any other values. This is another field from Pine Tree Research Station that we evaluated in 2019. We have lots and lots of different nitrogen treatments out here and different nitrogen timings in this field, and you can see the large differences in the intensity of greenness among these different plots. I want to zoom in on this portion of the field and take a little bit closer look at it. And in this portion of the field we have 6 different nitrogen application rates, ranging from 0 all the way up to 270 pounds of nitrogen applied per acre. And for each of these small rectangles here, we determined the DGCI value, the dark green color index value, and it ranges from 0.36 for the 0 all the way up to 0.66 for our highest nitrogen application rate. I think one thing that's really interesting is visually I cannot tell any difference between the 90 all the way up to the 270. But if we look at the DGCI value, we see that those steadily increase, including up from 0.57 for the 90 up to 0.66. So it gives us something that's much more sensitive than our eye in determining the nitrogen that it has received. You'll also notice in the upper left-hand corner these yellow and green boards. We in the past have used those as kind of internal standards so that we can correct for differences in lighting conditions that may affect the DGCI value in the field. We have since determined that we can use the dark green color index value for our highest nitrogen treatment, and
we can express all the other DGCI values using this as kind of an internal control. Makes it much less difficult, especially for in the future a producer who may just need to have a high nitrogen portion of his field, a high nitrogen strip that he can relate to in the field. I mentioned earlier in the presentation that in addition to looking at the DGCI value for determining if corn needed additional nitrogen, we were also looking at leaf nitrogen concentration that was taken from vegetative corn between V8 and V12. And this is what we found with that analysis. We're looking at the relative grain yield here versus the leaf nitrogen concentration. And what we find is that as the leaf nitrogen concentration increases from around 1% up to 3%, we see a steady increase in relative grain yield. And once we are above around 3%, we see no further increase in relative grain yield. So this has been a big step forward in helping us understand the response of relative grain yield to leaf nitrogen concentration. We've done similar kind of analysis with the dark green color index. It's a little bit more complicated. And in this figure, we're looking at the relative grain yield again, and we see the dark green color index here. But we also have this other third dimension, the reference dark green color index, which corresponds to the high nitrogen strip in the field. But what we see is when the dark green color index is high, relative grain yield is high, and that decreases as the dark green color index decreases. This is also modulated somewhat by the reference dark green color index from the high nitrogen strip. Our next step in this research is to calibrate how much nitrogen needs to be applied to corn between V8 and V12 based upon this dark green color index, and that is research that is ongoing and that we're working on now. I want to thank the Arkansas Corn and Grain Sorghum Board for their support. Dr. Roberts and I certainly appreciate it, and we'll be glad to answer any questions. Thank you very much.